The initial mass of a rocket is 1000 kilogram. Calculate at what rate the fuel should be burned so that the rocket is given an acceleration of 20 meter per second. The gases come out at the relative speed. Okay, all right. See, this question is something which represents the class of problems which we classify as variable mass problems. As the variable mass problem, well, there can be many examples. One is the the conveyor belt problem, right? The conveyor belt problem, and the other is the man or the weight dropping trolley problem, and the third one is the rocket propulsion. We'll discuss all three cases here, or as and where the question comes up. So first, let me take you through the basic terminologies of rocket propulsion. So I'll tell you what's going to happen in this discussion. We will go through the basic terminologies, okay, and then we'll apply the impulse momentum theorem, okay, and then we'll find out the application, or we'll find out the application of this concept in the question here. Okay, so basic terminologies, then impulse momentum theorem, and then the application. Now, see, if you can spend a couple of minutes here to understand what's given here, then the whole derivation process and the application would become really clear to you. Just if you spend some additional time in understanding the description here. So what I've done is a rocket is being propelled from the ground. Okay, so this actually refers to the ground level, and there is a person standing here. So he's observing all these things, and he has a camera with him. What does he has? He has a camera with him. So the rocket is going up like this. Okay, what he does is he takes two photographs. One after the launch at time t is equal to t, and the other very soon after t, but with the interval delta t. So the rocket was going like this. One photo was taken here, and the other photo was taken here. So now what we have is we have two different photos of the same rocket at two different time intervals. Time is equal to t, and time t is equal to t plus delta t. Okay. Now, assume that the initial velocity of the rocket is u0. Well, it can be 0. And it can be some definite value as well. That's something we'll discuss while we go to the numericals. Okay, so the object may have an initial velocity which is not equal to 0 or maybe equal to 0. The initial mass of the rocket is m0. So what is the initial mass of the rocket? Initial mass of the rocket actually means mass of rocket plus the unburnt fuel. Okay, now as the rocket is going up, we know that velocity of the fuel will give a additional push to the rocket, which will increase the velocity of the rocket, right? So consider two fuels here. One is represented in blue color, the other is in the red color. Okay, now when one fuel is burned completely, say for example, one fuel is burned completely, the rocket experiences a push, it is acquiring a velocity of vr. Now I have used the velocity vector here and not the magnitude. So this is velocity vector vr. Okay, so what is vr? Vr is actually the magnitude of the velocity vector vre, which means velocity of rocket with respect to earth. Okay, so what is vg? Vg is the magnitude of the velocity vector vge, which means velocity of gas with respect to earth. After some time dt, we see that the additional mass rocket, the mass has also been burnt. Okay, so say the burnt mass of the fuel is dm. The mass of this point of the rocket was m. So now we can say that the burnt fuel has reduced. So we can say that the new mass is m minus dm, right? And the velocity acquired, there will be a minor change in the velocity, which we can say that velocity of rocket plus delta v, both in the vector notation. Okay, now having said this, please go through this terminologies one more time, and take your time, take a minute or maybe a couple of minutes, go through this terminology, because the more and more you understand what these basic terminologies are, the better you will have understanding regarding the derivation, or for that matter the solving the numerical. Okay, so now what we'll do is we will try to understand those two photographs in detail. So this was the first photograph, time taken at t. The other is time at t plus delta t, this one over here. Now we will consider a system here. What is the system? the rocket plus the gases. We'll consider system here. What is the system? Rocket and the gases. So we have one system at two different points, t and t plus delta t. Velocity of the rocket here is v, the mass is m, well, it's velocity vector vr, and velocity of the rocket after some time is velocity of rocket plus delta v, both in vectors, and the released gas have velocity of vg. Okay, the mass was m, the mass of rocket here would be m minus delta m, where what is delta m? Delta m represents the gases burnt. Delta m represents the gases burnt. In which case, since the overall motion of this object is, or the system is governed only by the internal constituents here, we can say that the F external acting on this is equal to 0, and therefore by the principle of conservation of linear momentum, we can say that the final momentum is equal to initial momentum, right? Now the final momentum will definitely have two components. One will be that of the rocket and the other will be that of the gases. So the final momentum will have two components. One will be that of the rocket and the other of the gases, and so will be the initial momentum of rocket plus initial momentum of gases. This is the initial condition. In the initial condition, the rocket will have, the initial rocket will have m and vr. The gas will have zero velocity, right? So here the velocity of gases is actually equal to 0, and therefore we can say that which gas, I've taken only the red one here, which means the red is still stationary, the velocity is 0, therefore this term will become 0. Now coming to the final component, what we have is final momentum of rocket is actually mass of rocket into velocity of rocket. The final mass is m minus delta m. Velocity is vr plus delta v plus momentum of gas is actually final momentum of gas will be equal to final mass of gas, which is delta m, into velocity of gas, which is vg plus vg. So this is the equation what we have here, right? Okay, now okay, I think there is, give me a minute. Okay, so now here we'll try to do the algebraic steps left over here. So what is m into vr? It is mvr, all of them in terms of vector notation. M in delta v is m delta v, minus delta m into vr, minus delta m vr, minus into plus again minus delta m delta v plus delta m vg is equal to mvr, all of them in vector notation. So if you observe this equation, we have two terms common on the LHS and the RHS, which means that we can remove these two terms, right? And all we're left is with m delta v minus delta m vr minus delta m delta v plus delta m vg is actually equal to 0. Okay, so let me take the next set of equations. What we'll do is we'll keep this m delta v on the LHS and we'll transpose each and every other term to the RHS. So delta minus delta m becomes plus delta m vr, minus delta m delta v becomes plus delta m delta v, and delta m vg becomes minus delta m vg. See, now what I'll do is I'll divide this entire equation by delta t. And delta t, and delta t. Okay, now here comes the first level of concept here. As delta t tends to 0, we know that by the logic of maths, right? I think we have discussed this many times in motion in a straight line, the tangent, secant, how this is dy by dx becomes, delta y by delta x becomes dy by dx. We discussed that many times. So delta v by delta t becomes dv by dt, delta m by delta t becomes dm by dt. Now, what we also need to understand is, as the mass burnt in delta t is negligible, time is negligible, we can say that delta m can be neglected, as delta m would be equal to 0, or will tend to 0. Okay, or we can also say that change in velocity in this time delta t is also equal to 0, or in other words, as delta t tends to 0, delta m also tends to 0, and delta v also tends to 0. Or let us say for example, say this is 0.000013 seconds, and this is equal to 0.000014, and therefore what will be delta m in delta v? that would be 0.00000, very, very, very small number. Therefore, what we can do is we can neglect this entire thing over here. We can neglect this entire thing, which means we can neglect this term. We can neglect this term completely, and therefore, if we remove this term, we are left with only two terms, which is on the RHS, delta m delta t becomes dm by dt, delta m by delta t becomes dm by dt, and LHS is delta v, which becomes dv by dt. Okay, now let us focus only on these set of equations. Now, so okay, now many students find it confusing over here. So what I'm going to do is I'm going to spend a little more time to explain the basic derivations from motion in a straight line. See, relative velocity of vector A with respect to B is actually velocity of A vector minus velocity of B vector. Okay, well, not R, V. And we also know that velocity of vector A with respect to B is actually equal to minus velocity of B with respect to A, right? So these three things are very basics. I know someone who is following this at JEE mains level would be very thorough with this, but I just wrote it because I don't know, many students would come from different backgrounds. So this concept is really important here. This step is very important. Now let us see. I'll take dm by dt common from these two terms. So we have dm by dt and Vr and Vg. So dm by dt into Vr minus Vg. Again, Vr is vector. So what is vector R minus vector G? See, vector A minus vector B is vector A with respect to B, right? So vector R minus vector G would be vector R with respect to G. All right. Now, what is vector A with respect to B is equal to? That is equal to minus vector B with respect to A. And therefore, we can say that this is actually equal to VRG, which is actually equal to negative of VGR. So, VRG is equal to negative VGR. Now, what is velocity vector, the derivative of velocity vector? There is acceleration vector. What is velocity of derivative of velocity vector? It is acceleration vector. So this term can be replaced by AR. So this is m into AR. M into AR is equal to dm by dt into minus VGR. Okay. Now what is m into AR? So if you have to understand this practically, what is velocity vector? VR is the velocity of rocket. What is AR? AR is the acceleration of rocket. So what is m into AR? It is mass into acceleration of rocket, which is actually the force acting on the rocket, and therefore we have the force acting on the rocket is equal to dm by dt into minus VGR. And since this is due to the action of the gases burned, we don't call it VR, we actually use the notation F thrust. Okay, so F thrust is what we have, dm by dt into minus Vg by VR. And all of this is in the vector notation. Now, if we try to understand this using the scalar notation, what we have is, if we take magnitude on both sides, magnitude of F thrust becomes F thrust alone, and dm by dt is magnitude, and vector minus VGR, if you take the magnitude of this vector, if you take the magnitude of minus VGR becomes VGR, and therefore F thrust is equal to dm by dt into VGR. Okay, so I hope this much is clear. Now, okay, let me explain you this concept of how to use scalar notations here, because some of you may find it convenient using the scalar notation. I'll explain you that concept as well. What is that? So a man is standing here, he is observing the gases and he is observing the rocket. All right. So when he is observing the gases here, he is observing the gases while standing on the ground. So he's observing the gases while he is standing on the ground, and therefore what he sees is velocity of gases with respect to Earth. So this is Earth. Okay, one more time. This man is observing the rocket, but where is he standing? He is standing on Earth. Therefore, what is he seeing? He is seeing velocity of rocket with respect to Earth. Okay, But if you shift the same man and put him on the rocket, then when he is observing the gases here, he is observing let me use different color. So he's observing the gases. He's observing the gases, but where is he observing it from? He's observing it from the rocket, and therefore what he sees velocity of gases with respect to the rocket. All right. Okay. Now, what is velocity of gases with respect to rocket? It is equal to velocity of gas with respect to Earth minus velocity of rocket with respect to Earth. Now, if you understand the concept here, velocity of gases, see, any vector vector A can be written as the magnitude into its unit vector. Okay, so vector B can be written as its magnitude into its unit vector. Now, if you understand the motion of this rocket, it is going to the straight direction. It is going vertically up, right? So vertically up from Earth would be positive, and vertically down from Earth would be negative. Since it is vertically up, we'll take it as positive J. We'll take it as, oh, give me a second. We'll take it as positive J and minus J. So gas with respect to us, gas is coming downwards, so we'll take it as minus J. Rocket is going upwards, so we'll take it as plus J. And if since there is more, okay, so now if you expand the bracket here, this becomes minus Vg into J cap minus Vr into J cap. If you take minus J common, this becomes Vg plus Vr into minus J. And if you take magnitude on both sides, this becomes magnitude of vector Vgr, which is actually equal to Vgr, is equal to Vg plus Vr into minus J. Now something else as well, which is the very simple concept. See, this is velocity of A and this is velocity of B. What is the angle between them? The angle between them is theta is equal to 180 degree. So what will be the relation, the resultant velocity? The resultant velocity, or what will be the resultant speed? It will be equal to the sum of these two velocities. Straightforward, right? Now, in the other case, if this is VA, if this is VB, what is the angle between them? The angle between them is 0. In this case, what will be VAB? That will be equal to VA minus VB. So we have discussed these concepts many times and repeated this in almost every numerical that we discuss in motion in a straight line. Okay, so this is the equation what we need here, which is F is equal to dm by dt into minus VGR in the vector notation, and in scalar notation, F is equal to dm by dt into VGR. Now let us try to solve the question. So what did we derive so far? The magnitude of, okay, let me write that as well. So the vector F thrust is actually minus V relative into dm by dt, right? And the magnitude of this vector is Ft is equal to V relative into dm by dt, right? Okay. Now let us consider the free body diagram of the rocket. Where in a scenario where there is a presence of a gravitational field, unlike in free space. So when there is a gravitational field, we know that there will be two forces, one F thrust and the other what will act on it? Mg. So we'll write it over here. F thrust will act upwards and Mg will act downwards. So if you have been following the assigned convention as we did in the previous questions, we know that the net direction of motion is upwards. So all those forces which are acting upwards would be taken as positive. The net direction of motion is upwards, and all those forces which are acting downwards would be therefore taken as negative, right? So if we have to apply the Newton's laws of motion, we can write that sigma Fy is equal to m into Ay. So we can write m into Ay is equal to sigma Fy the other way around. So we can write ma is equal to, what is sigma Fy? Sum of the forces, which is plus Ft, right? Which is plus Ft minus mg. So it's plus Ft minus mg. If you transpose mg to the LHS, what we get is ma plus mg is equal to plus Ft. What is Ft? V relative into dm by dt. And what is mm? We can take common here, so we can mass is 1000 kilogram. So it's 1000 into what is acceleration? 20 meter per second square plus what is g? The value of g is 10 equal to what is v relative? Relative speed of 500 meter with respect to the rocket. So this is 500 into 500 into dm by dt. So basically what we get is dm by dt is equal to 1000 into 30 the whole upon 50. So wait, 1000 kilogram meter per second square. Okay, so now this thing gets cancelled, so it is 3000 by 50, and therefore dm by dt is equal to 60 kilogram per second. Okay, a lengthy derivation is the reason why the solution took so long. See, if you write only this much as a solution, then things become really complex, because you may be wondering why is it ft negative, and then why is ft positive here, and then why did we take ft as positive and mg as negative. So all this confusion would arise while discussing only the solution here. That is the reason why I have explained the derivation in detail. I've explained the terminologies in detail. I'm sorry if I made the content go a bit broader. So hopefully you understood it. Let's go to the next question, in which case, which is based on force and acceleration.